So there's several application problems at the end of your homework. And most of them actually give you the differential equation. And your only task is to kind of figure out which letters in the differential equation stand for what and go ahead and solve it. But they do give you one mixing problem, which is kind of a classic differential equations type of problem. And they do let you work out the differential equation on your own for these. And it's a good way to sort of break into the idea of using a differential equation to describe a real life situation. So let's see what's going on here. This is 40. You've got 39, which is actually a little bit simpler. 40 says you've got a tank containing 1,000 liters of pure water. Brine means salt water. Brine that contains 0.05 kilograms of salt per liter of water enters the tank at 5 liters a minute. And then there's also brine coming in that contains 0.04 kilograms of salt per liter that enters the tank at a different rate. And then they keep the whole thing mixed up really well. And then they're draining from the tank at 15 liters per minute. Notice they've got like 5 going in and 10 going in, 5 going in and 10 going in, 15 coming out. So at least the amount in the tank is staying the same. How much salt is in the tank after T minutes and after 60 minutes? On first glance, this might seem like just an algebra problem, but if you start thinking about it, you say, yeah, there's some salt coming in, some more salt coming in, but there's also salt going out. And the salt going out is just the result of the mixture of however much is in the tank at that time. It's a little bit difficult to just write down an equation for the amount. It's going to be easier, it turns out, to describe the rate of change in the amount. So I always like having a picture for these things. And not just because I can actually draw tanks. Sort of. So there's my tank. Nice circular tank. And let's see, we've got some brine coming in. So here's one pipe. Putting some brine into the tank. And there's another one over here. It's also putting some brine into the tank. And then I guess I should have made a pipe over here. And the mixture's coming out. And it's kept well mixed. So let's put a little mixer in here. Some kind of little propeller thing. Okay, good enough. So it's being kept mixed. Okay, so the big key here for mixing tank problems is to say the rate of change in the amount is equal to the rate in minus the rate out. Okay, so let's see if we can set that up. So let's say that the derivative of the amount function with respect to time is equal to the rate in. Okay, let's go on with the rate in. Some is coming in 0.05 kilograms per liter at 5 liters per minute. So we've got a 0.05 times 5. We've got some more coming in at 0.04 times 10. So those are pretty straightforward. What's going out, though? How much? So keep in mind we're describing the amount of salt going in and the amount of salt going out. And that's what we're trying to describe the change in. Okay, the amount going out is however much is already in there total divided by 1,000, right? So that's how much per liter is currently in the tank. And they're pumping out 15 liters per minute. So notice each one of these is kilograms per liter times liters per minute, including this one. We've got A kilograms in the tank. That's what A is designed to describe. A divided by 1,000, so that's per liter, and then 15 liters. Okay, so let's see if we can go ahead and set this up and crunch it out. So these multiplications are pretty easy to do. We've got 0.25 and 0.4. So actually here, let's just crunch that together to 0.65. So 0.65 minus 15A over 1,000 equals dA dt. Okay, differential equation is set up. I should point out we actually have an initial condition here. It says at the beginning, the tank contains 1,000 liters of pure water. So the amount at time 0, the amount of salt in the tank is 0. So we do have an initial condition that will let us solve for the C eventually. But let's go ahead and see what we can do about solving this differential equation. So we really only have one technique so far, which is separable differential equations. So hopefully this is separable. I'm going to start by multiplying both sides by 1,000 just because I don't like that fraction, or that decimal for that matter. So I'm going to move over here. We've got 1,000 dA dt equals 650 minus 15A. I am going to divide both sides by 650 minus 15A and multiply both sides by dt. Oops, still a dA here. Okay, technically there's still a 1 on this side, I guess, when I divided both sides by 650 minus 15A. But okay, I am separated, and I am ready to do a, let's see, can I separate that or simplify that fraction at all? I guess I could divide a 5 out of the top and bottom. So let's get 200 over 130 minus 3A dA equals dt. And we are ready to attempt to integrate both sides. On the left-hand side, I'm going to factor the 200 out of the integral. So I've got 200 integral 1 over 130 minus 3a dA equals integral of 1 dt. The left-hand side needs a little u substitution. which I'm going to skip. And we, again, technically have solved this differential equation. It still needs a little bit of cleanup. We need to figure out what C is, and if possible, it'd be nice to solve that thing for A. So we had a function that says A equals. So let's see if we can keep chugging on this thing a little bit, but I need to get myself a new screen. Okay, so keep in mind that we had A of 0 equals 0. Let me go ahead and get that jotted down again. Oops, still attached to that. Hold on. All right, we had A of 0 equals 0. That means we can solve for the C right now. So let's go ahead and do that. Plug in 0 for time and 0 for amount. So at time 0, when t was 0, then the amount of salt was also 0. So plug in 0 for A, and we get 200 over -3 times natural log of 130, which is some decimal. I'm actually just going to leave that exact for the moment. So we know that C is 200 over -3 natural log of 130. So the full equation looks like this. And I do want to go ahead and solve this for A. So a couple more steps. So we actually have a function that says the amount equals. So let me go ahead and multiply both sides by -3 200ths. So that cancels here, obviously. Natural log of 130 minus 3a equals -3 200ths t plus natural log of 130. We do need to exponentiate both sides now. E. So 130 minus 3a equals E to -3 200ths t, and then this would also be E natural log of 130, so that would change into a multiple times 130. And thankfully we're pretty close to being done with this monster problem. Let's add 130 to both sides, so we'll get -3a equals 130e to the -3 200ths t. I just changed the order on those two things, and then we're adding 130 to both sides, and finally we'll divide both sides by -3. So there finally is my function that describes the amount of salt in the tank at any given time. And we can use that to answer the couple questions that, or the one question, I guess, when they asked about plugging in 60 for time. Which I think, if I remember right, when you plug in t equals 60, then the amount comes out something like 25.7-ish. I looked, but I can't remember now, kilograms. But anyway, you can plug in that t equals 60 to get that answer. All right, I think you are, like I said, the problem that you have assigned in the homework is simpler than this one, but I think you're fully ready to tackle it now.